All right, I believe we are recording. Good afternoon. My name is Ronald Benbow, and I am presenting here live from Pierre, Michigan. Happy fall, and welcome to week 6. I'm going to explain and present our advanced presentation topic for week 6, which is regarding the atomic bomb, and more specifically, describing nuclear fusion. All right, so let's go ahead and get started. There we go, got it. All right, so big picture. For this week's topic, I split it off into 3 important components. First, defining what thermonuclear fusion is and how it's applied to the practical application for the video of describing the process of a hydrogen bomb or atomic bomb or thermonuclear bomb. So first, we're going to go over some terminology, defining what certain terminology is and how it's applied to this week's topic. The second step is going a little bit more into the reaction as it relates to this week's topic. And then last, we'll talk about nuclear fusion, the components. So important components that help describe how this process happens as it relates to bombs or the atomic bombs. There we go. All right, so let's get started with the first topic, and that is going to be thermonuclear fusion. So the best way to define this, thermo, meaning heat or dealing with temperature, nuclear, nuclei, and then fusion, think about things fusing or being held together or combining to meet and combine to one. So that's where we come to fission versus fusion. Fission, as we discussed earlier this week, is where an atom or molecule is split into multiple components of itself, leading to different components or elements over time. Whereas fusion is the opposite of that. As mentioned before, is where 2 nuclei fuse or come together as one. Hence the word nuclear fusion, 2 nuclei, 2 or more nuclei come together and fuse as to one particular molecule or element. And then thermonuclear is pretty much the same thing, but this time we're taking that same concept, but this time it deals with how temperature is involved with nuclei, fusing these atoms or nuclei together. So nuclei fuse together, thermonuclear fusion, same thing, but this time it's where temperatures evolve to cause those 2 molecules or atoms to fuse together. Also, another interesting word that came up, and you may have seen in other science classes or hard science classes, plasma. In my case, I think of plasma from the physiological perspective, but this is different in a sense for this particular course, where plasma, in this case, in chemistry, is where ions and electrons are floating around in the form of a cloud or a gaseous state. And we'll talk a little bit more in depth why that has something to do with thermonuclear fusion. So inside the reaction, so think of it as a 2-step process. We have fission, where these little atoms and molecules, elements break apart and divide. And then you have fusion, where the particles or little nuclei that are out there in the universe find a way to combine, and when they react, combine together. So in a sense of thermonuclear bombs, the first step is fission, So fission happens, and then after the explosion, energy is released. And when that energy is released, temperature increases, which speeds up the process of those tiny, tiny nuclei to combine together or fuse together. So that describes the 2-step process within our practical sense of a bomb. So what's important, since we described what the difference between fission and fusion reactions are, in this case, there are 3 important components to help stimulate that process. So the first and very important step is temperature. You need a high degree temperature in order to get this process started or to initiate fusion of these nuclei to combine or come together. So having a very high temperature is key. The next step is, in addition to high temperature, the ions must be confined with a high level of ion density to achieve the fusion reaction rate. And I described that a little bit more in depth in the third step. So the third step is where the ions, which have to be held together, but this time we have to factor in the distance. So they have to be held together in a very close proximity at a very high temperature with confinement and within time that's long enough to avoid temperature cooling. And that's why temperature and proximity are very important and considerate of the third step, because once the temperature drops, then that can compromise the whole fusion process. So temperature, very high temperature, having a high ion density for them to achieve the fusion reaction rate, and also being in close proximity with the high temperature and close distance to one another to cause fusion to happen within a timely manner. Very complex. Now, as we relate this to back to the hydrogen bomb, one particular element that's important for this particular case is the lithium deuteride solid, or LID. I may have said that wrong, but LID, which is a solid element, helps cause this whole fusion thing happen in 2 steps. So the reason why LID is used in solid form is because it's able to be tightly packed inside, let's say, the capsule or the bomb. And this is where the first step is initiating fission. So you have all that fission reaction going on inside this tight little compacted space. And then once that explosion happens, we know that energy is released. And when that energy is released at a very high temperature and within close proximity, from that explosion, that's where fusion is promoted. That's where the little nuclei bind together or fuse together, hence thermonuclear fusion reaction. So I hope that makes sense. I meant to talk about one more thing, and the kind of jumping back to how close proximity and ion density, what components can help stimulate that process. In some other areas of thermonuclear fusion, you may have heard magnets. Magnets are very useful to keep hot plasma confined with its powers. Because in plasma, ions and electron density, they cannot pass through a strong magnetic field. So having a strong magnetic field can help regulate the hot plasma that's confined. And then secondly, we have the lasers. Lasers can be used to cause an inertial confinement fusion. So at max density and at rapid compression, and also temperature, high temperature, lasers can help stimulate that process, but there's still more research that needs to be done on how to control that a little bit better. But other than that, I just want to chime in back on that. Thank you so much for your time. I hope this made sense. And my name is Ronald Bimbo, reporting here live from Michigan, and I am signing off. Have a great weekend.